Hi, my name is Tanya. Me and my colleague Manuel will provide you with a short introduction into the concepts behind rapidFLIM, the setup used for it, and an application example.
Hello, my name is Manuel Veiga, and in this video today I will show you a new approach to FLIM developed by PicoQuant. So up to now in FLIM, you had to decide whether you're going to have fast acquisition or quantitative data. But this decision you don't have to make anymore because you can have both by using rapidFLIM.
Our rapidFLIM approach allows recording several full FLIM images per second by using our new TC-SBC board TimeHarp 260 Nano in combination with a detector from our PMA hybrid series. This hardware combination allows detecting many more photons within a given time span compared to conventional FLIM measurements. Thus, with a slight sacrifice in temporal resolution, the new TC-SBC electronics can work at much higher count rates. In contrast to frequency domain FLIM, the high optical resolution of confocal microscopy and ease of use is available with rapidFLIM. Depending on the sample brightness and image size, FLIM data acquisition can now be sped up to more than 10 to 15 frames per second compared to classic FLIM image acquisition that takes at least 30 seconds for one frame. This way, rapidFLIM enables accurate observation of fast processes or rapidly moving species. On a confocal scanning microscope, a FLIM image is acquired by scanning the pulsed excitation laser across the sample. Photons are recorded with single photon counting detectors and processed with the timing electronics. Using line and frame markers provided by the scanner, the spatial origin of the photons can be determined and all counted photons are sorted into their respective pixels for further image analysis. In the case of a fast scanning system, this very often leads to only a few detected photons per pixel, which will not allow proper FLIM analysis. In order to decrease the acquisition time for rapidFLIM, the count rate at the detector must be increased so that more photons can be recorded per second. This, however, leads to two important issues that affect the TC-SBC histogram and the fluorescence lifetime results, namely the instrument dead time and the pile-up effect. After registering an incoming photon, the system is busy with data processing for a certain amount of time. This time period is called dead time, and any photons reaching the detector during that time will be lost as they cannot be detected and processed. At high count rates, most photons will not be recorded due to the dead time, leading to a phenomenon called the pile-up effect. In this case, only the first photon arriving at the detector in each excitation cycle will be collected. This in turn leads to an overrepresentation of early photons in the statistics. The TC-SBC histogram is skewed towards shorter arrival times, and the calculated fluorescence lifetimes will be shorter than in reality. To avoid the pile-up effect in conventional FLIM measurements, the count rate must be reduced that statistically only one photon after every 50 to 100 excitation cycles is recorded. This, in fact, leads to long acquisition times. In our new rapidFLIM method, this measurement artifact is eliminated by using detectors and TC-SBC electronics with very short dead times. Thus, more photons are recorded over the same time span than in a conventional FLIM experiment, and no late photons are lost. Consequently, higher count rates can be achieved to speed up data acquisition. In this example measurement, the diffusion of two kinds of dye-labeled beads are monitored with rapidFLIM. The method is fast enough to follow particle motion in solution. The large beads were labeled with Nile red exhibiting a fluorescence lifetime of 3.3 nanoseconds. The smaller bead population contains the dye dragon green with a fluorescence lifetime of 4 nanoseconds. Photons emitted by the dye-labeled beads are collected by a detector from PicoQuant's PMA hybrid series. The detector's output signal is split into two identical parts. Each part is fed into either a conventional TC-SBC unit or a TimeHarp 260 Nano with short dead time. The left viewport shows the image obtained with the conventional unit, while the right one shows the one from the TimeHarp 260 Nano. The fast FLIM contrast in both images represents the false color coded average photon arrival time. Short lifetimes are color-coded in blue, whereas long lifetimes are shown in red color. The brightness is determined by the number of photons in each pixel. In the rapidFLIM measurement on the right side, the contrast is sufficient to clearly differentiate between both dye species, which have a lifetime difference of about only 700 picoseconds. By comparison, the contrast is much lower in the conventional FLIM image on the left side, and both bead types have a similar greenish color. This difference in fast FLIM contrast and lifetimes is due to the pile-up effect described previously. Because of its dead time, the conventional TC-SBC board cannot process all arriving photons. This can be easily seen by comparing the peak count rates in both images.
The conventional electronics report about 19 kilocounts per second, while the TimeHarp 260 Nano sees about 38 kilocounts per second.
The skewed statistics arising from the lost photons leads in turn to the observed lifetime shortening and to the reduced fast FLIM contrast when using conventional TC-SBC electronics. To avoid this pile-up effect and measure correct lifetimes, the detection count rates in classic FLIM acquisition should be well below 10% of the excitation rate. Since in this experiment the excitation laser is running at a repetition rate of 50 MHz, the detection count rate should be below 5 megacounts per second. This limit is indicated in the time trace by a red line. Thanks to hardware components optimized for short dead times, our rapidFLIM approach can still provide excellent results at high detection count rates. This makes it possible to speed up FLIM image acquisition while maintaining good spatial and temporal accuracy. Outstanding applications of our rapidFLIM approach would be studying fast thread processes such as transient protein interactions, detecting molecular interactions in rapidly moving objects like in endosome trafficking, or dynamic changes of environmental parameters. For example, the ion flux, pH value, or oxygen concentration. This method also provides the opportunity for fast three-dimensional FLIM measurements, live-cell FLIM observations to follow, for example, the metabolic state, and enables high-throughput FLIM screening.